is the initial metabolic pathway that converts 6-carbon glucose into two 3-carbon pyruvate molecules in a 10-step process broken down into 2 stages. The first stage is the hexose stage that consumes energy, and the second stage is the triose stage that produces energy. There are 3 metabolically irreversible steps where glycolysis is regulated, and the product of glycolysis, pyruvate, has 3 different fates depending on the absence or presence of oxygen. The net equation is glucose, 1 molecule of glucose in 2 ADP molecules, 2 NAD plus molecules, and 2 inorganic phosphate molecules that are converted into pyruvate, 2 ATP, 2 NADH, 2 H2O, and 2 protons.
In the 10-step process of glycolysis, there are 10 enzymes that are required to yield us our 2 3-carbon molecule pyruvate. Our first enzyme is hexokinase. That is a rate-limiting molecule that commits glucose to the glycolytic pathway. Our second enzyme is glucose 6 isomerase. The third enzyme is fructokinase 1. Our fourth enzyme is aldolase. Our fifth enzyme is triophosphate isomerase. Our sixth enzyme is glyceraldehyde 3-phosphate dehydrogenase. Our seventh enzyme is phosphoglycerate kinase. Our eighth enzyme is phosphoglycerol mutase. Our ninth enzyme is enolase, and our 10th enzyme is pyruvate kinase.
Just like any metabolic process, there are regulation checkpoints in which the cellular process has to be maintained. For glycolysis, there are 3 regulation checkpoints that are used. The first one is glucose 6-phosphate formation, where the enzyme controlling that is hexokinase. The second checkpoint is fructose 6-phosphate that turns into fructose 1,6-biphosphate, and that is controlled by PFK1. And for the third regulation step, that is when PEP turns to pyruvate, and the enzyme controlling that is pyruvate kinase. I'll be focusing more about the second step, where PFK1 is affected. As you can see by this chart here, if there is an abundance of citrate or ATP, it would deactivate PFK1, therefore slowing down glycolysis. If there is an abundance of AMP or fructose 2,6-biphosphate, that will activate PFK1, therefore turning on glycolysis. You can see these processes being similar in the first step and in the third step. And this is how we maintain glycolysis in this cycle.
Following glycolysis, pyruvate is a product that is a crucial intermediate for many catabolic and anabolic pathways. For catabolic pathways, the next step is dependent on oxygen concentration. Under anaerobic conditions, prokaryotes convert pyruvate into ethanol via alcohol fermentation, whereas eukaryotes convert pyruvate into lactate, which does not immediately yield energy. Under aerobic conditions, eukaryotes proceed towards Krebs cycle, yielding some energy in electron carriers. For anabolic pathways, pyruvate can be converted back into glucose via gluconeogenesis. Other anabolic reactions include indirect synthesis of amino acids. Finally, lipid and fatty acid synthesis also uses pyruvate as an intermediate, making this molecule central to many pathways.